Now, again, we are still on the parts of casting, the mold for casting. And in the previous slide, I told you that this is more or less complete design, but there is some other nomenclature. And here I have shown just one more an image. What kind of structure you're going to get after you pour the metal? The yellow color is the metal. You also can call it charge. There are also nozzles. So this is a little more sophisticated design compared to the previous schematic that I had shown to you. So here you can also see that the metal is being poured from the center, and now we are not making just one structure, but we are making two such structures. And yes, this can be done, right? You can even combine multiple structures in series and you can fill them all together. Two structures is very common. People often make two structures together, and then this is how it looks like. You pour the metal in the center and you have two runners, and it is connected to two structures. Okay, so this is another this is a more detailed. So here also you see things like ejector pins and so on. So pouring here is done from the middle, from the center, in both channels simultaneously, and then according to whatever shape you want to make. Also the overall cast will also require some pins which are closed and opened, because you need to, even the two parts, the cope and drag, when you connect them with each other, you need to make sure that this is tightly held during the cast, when you're pouring the metal, because also when you pour the metal and then it suddenly solidifies, there are hydrodynamic forces which can even shake your entire structure. So you want to avoid all of that. That is why everything should be tightly packed and nicely held together. So you will also have different types of pins and clips, and two ejector pins I have shown here also to eject the structure afterwards, right? Because you need to just, these are things that make the process easy, and they very much depend on the type of mold, the material that you have used for the mold, and also the type of structure, how complicated it is. Sometimes you can also make hollow structures using casting. Because there what you can do is, if you want to make a hollow structure, then you put some something in the center. Let's say a cylinder. If you want to make a cylindrical hollow shape, so you put a cylinder in the middle of the cavity, so the metal will only be filled around it and not inside the cylinder. Then you remove the cylinder. So you can also make basically complicated hollow shapes and all these things using casting process. Okay, so now some more details. I told you that there will be some shrinkage when we perform the casting process. And why do we have this shrinkage? Not very difficult, because we are solidifying the liquid metal. So it is expected that the atoms will come together and the crystals will be formed, and then you will have some volume. Overall volume is a little bit reduced. So that is why you're going to get some sort of shrinkage. That shrinkage can lead to porosity in your structures. So this is what your structure is, and maybe in the center, because there was shrinkage, then in the center I get this pore. Now, can somebody think of this? Why do we have this gap or the empty space in the center and not in a corner or something like that? Well, there is a reason for it. The reason is that your metal starts to solidify from the walls. If you fill heated metal or heated anything in a glass, then what will happen? Don't think that it will not solidify top to bottom or anything. It will always first solidify close to the walls, all the walls, bottom wall also, if there is so whatever is the surface. That is why, because the walls are at room temperature. The walls are at the outside temperature, and they are the coldest regions in that entire structure. So what you are going to get is something like this. First, so this is the structure. Let's say top and bottom there are two walls. And then you see that the metal starts to crystallize. Solidify means crystallize, because metals and alloys are crystalline materials. So they will form these kind of longer crystals. They are known as dendrites, by the way, along the walls. And then these dendrites will grow towards the center. And if there is some volume shrinkage, then maybe at the center there is some little bit space left, because there was not enough material. Okay, what do you do in that case? In that case, the additional material comes from the riser. Your riser should have enough metal in liquid state at that time, that if after the shrinkage there is some little more metal or material is required, that can automatically, because of gravitation, because the riser is designed in such a way that this will flow down the metal will flow down and fill the cavity. So that is the idea, and that is why we need all of these different little parts, right? Okay, now you have your shape. Now it is solidified. What did you do? You now, after the shrinkage and everything, you remove the mold, and now what you have is your initial part, which will now be processed using secondary operations such as surface polishing. So these are called machining operations. We'll come to machining. Okay, so yeah, however, machining we are not talking right now, but one thing we know that also during this surface finish and machining and so on, you will lose some material. If you want to polish the surface, you remove some material, right? So there will be some material lost there as well. And also there may be some shrinkage in the, even though we are using refractory material, there may be some little bit of thermal expansion and then shrinkage because of the variation, very sudden variation in the temperature. So that might also happen in the mold. Now all of these things need to be factored in if you want to get the perfect shape, the perfect dimensions of your structure that you needed, right? Because you need to ultimately meet the manufacturing tolerances. If you're, for example, manufacturing a gear, and it needs to fit into the engine, it needs to, because it also needs to be a part of another large scale machinery. So you need to meet the tolerances. So in that case, what you do is you make your pattern, initial pattern, slightly larger than your final product. Why? Because you know that you're going to use some material afterwards in machining and due to shrinkage and all these things. And these allowances, the little bit of extra dimension, instead of 10 centimeter, you made it 10.1 centimeter. That is known as pattern allowance. So pattern allowances are for the purpose of taking care of all these losses. And there is also a formula for that, which I have mentioned here. If you have some casting dimension L, and alpha is your, for L dimension, alpha is your thermal expansion coefficient, and then you have freezing point of the material, and you have the room temperature defined as theta F and theta 0. In that case, this is how you define the shrinkage allowances. This is sort of a rule of thumb. Slight variations can take place, and one thing here in this formula you must notice is that shrinkage allowance also depends on the alpha or the thermal coefficient of the material. So for different materials, you're going to have different allowances. So it's not just the shape, not just the dimension, but also the property of the material itself that that tells you, or that determines what should be the shrinkage allowance for a certain pattern. Okay. Now coming to the mold materials. So this is, I think this is the last slide for today. Mold materials can be, I told you this, they are made, mainly you use sand, or what is known as green sand, we will discuss now. But other than that, you can also use refractory metals and graphite, I told you, various ceramic materials, alumina and so on. But usually there's sand molds. This is one example, same example, where you have sand mold, and inside that you have the pattern. Okay, fine. So now what you need, these are some of the steps. Again, I have mentioned, I also told you in the beginning, what is the idea altogether. What you're doing is you're taking a flask, and then you're making top half and bottom half separately. You place the pattern on top of it, half of it comes out, and then you close it, and then you remove the pattern. In some cases, pattern is also made of wax, by the way. That's a different type of casting. Next lecture maybe we'll talk about that. So what you do is, if your pattern is made out of wax, then you can just melt it and get rid of it, right? But there, of course, it's a one time. Every time you have a pattern, that can only be used once, right? But in the case of metal or wood pattern, you can use it multiple times. All right. So yeah, what did I do? Now I slowly, very nicely removed my pattern, and then I closed my mold back. And now what do I have? Now I have this cast that is made of sand. One thing here you need to definitely, or you must have already guessed, that this is not just normal sand. Now, if anybody has gone to a beach, people build houses, children build these houses. So the beach sand, you can see that beach sand is stable and you can make structures. The construction sand is not so good, it's very dry and also coarse, and you cannot make things out of it maybe. But beach sand is better. So you can even make it, you can further improve the properties of this sand such that it can hold its shape when we are doing this. You know, we are placing the pattern, then removing the pattern and all that. Okay, so this is why we need to have some additives in the sand. And also, you see, sand from different places has different composition, even different fraction of clay in it. So you need to have a standardized sand which can be used for particularly for casting purposes. That is known as green sand. Okay. Anyway, you have to remove the pattern. That is one thing you understand. For that purpose, you can also put some talc or powder on top of the pattern so it can be easily removed and doesn't get, you know, sand doesn't stick to it and so on. These little things are done. Okay. I also told you about these hydrodynamic forces when you have this really hot metal, 700 or 1000 degrees and so on, and it very suddenly solidifies. You're pouring this very hot metal inside. This can actually create so much hydrodynamic force that your entire cast can shake, vibrate, especially if you're making a small structure. So in order to avoid that, number one, you should have flask that is reasonably heavy and that does not shake and, you know, topples over, because that can also be very dangerous. And another thing you can do is you can also put a lot of weight on top of it. It's called dead weight. So you can also put some weight on top of that. Okay, so these are some small things. Coming to the composition of the sand, the green sand, it is a mixture of sand and clay and water and some additives such as wood powder or dextrin or sea coal. So this is the composition. Usually these additives are less than 6% in the overall weight, and above 80% is sand and the rest is clay and water and so on. Okay, so this is the composition of the sand, and this can also vary slightly depending upon what kind of structure you're preparing. Also, ferrous and non-ferrous materials and alloys typically have different, slightly different composition of the sand. Of course, also it depends on the temperature and so on. Okay, so these are some fundamentals of the casting process. We'll have a couple of lectures on casting. So more in the next lecture.